Hello, everyone. Today we'll be working on chapter 9, which consists of momentum, impulse, conservation of momentum, and rockets. Our first question, we'll start with non-long answer questions, then move on to the long answer questions. The first question says, true or false, a system with internal forces does not conserve momentum. This is false. A system with only internal forces means that it's an isolated system. In an isolated system, momentum is always conserved. The next question asks, what is the impulse on an object that has a force given by this thing, 3t in the x direction plus 4t squared in the y direction, and the force is applied from t equals 0 to t equals 3 seconds. We want to know the impulse. Well, impulse is a vector, and it's given by the force integrated over time. So in this case, the force is applied from 0 seconds to 3 seconds. So we integrate that from 0 to 3 seconds. So we just plug in our expression for our force here. And our limits, and then we just integrate each one. So our x part of our momentum is the integral over the x part of our force. So we know how to integrate that. The integral of t is t squared over 2. So we get 3t squared over 2 evaluated from 0 to 3 seconds. So at 0, it's obviously 0. And at 3, we just plug in our 3 here. So it's 3 times 3 squared over 2, which is 27 over 2, which is 13.5. So our impulse in the x direction is 13.5. It has units of force times time. This is Newton seconds, or equivalently, this is kilogram meters per second. The part of the impulse in the y direction is the y part of the force. So the 4 can come out, we just integrate the t squared. And so if we do that, we get 4t cubed over 3. Once again, evaluated from 0 to 3. So this is just 4 times 3 cubed over 3. So this is what, 36? Yeah, 36 kilogram meters per second. So our total impulse then is our 13.5 kilogram meters per second in the x direction, plus 36 kilogram meters per second in the y direction. All right, so our next question says, if the object from 2 is 10 kilograms, so our mass is 10 kilograms, and it started from rest, what is its velocity after the 3 seconds has elapsed? Well, we know that impulse is related to momentum. It's equal to the change in the momentum. Now, momentum is equal to mass times velocity. So our impulse then is our mass times our change in velocity. It said that we started from rest. So our initial velocity is 0. So this is just our mass times our velocity, which means that our final velocity is our impulse divided by the mass. Our impulse was this thing, so we just divide each one by 10. And so our final velocity is 1.35 meters per second in the x direction, plus 3.6 meters per second in the y direction. Let's see, our next question asks that a 2,000 kilogram car which is traveling 20 meters per second north, collides with a 1,500 kilogram car traveling 30 meters per second south. After the collision, the cars stick together and move as one with what velocity? So this is what's called an inelastic collision, or a completely inelastic collision. So in inelastic collisions, and this is a type of one, only momentum is conserved. So momentum is always conserved in any interaction where there are no external forces. So here, the only force that we have to worry about are between the cars when they collide. Now, eventually friction will slow them down, but we get around this by considering the velocity right after the collision. And the point is, though, that kinetic energy is not conserved. Only momentum is conserved. So if we sum over all of our initial momenta, it has to be equal to the sum over all of our final momenta. This is a one-dimensional problem because we have one object that's moving north and one object that's moving south. So let's use a coordinate system like this, where north is positive and south is negative. So if we draw our situation here, we have a 2,000 kilogram car, which is traveling north at 20 meters per second. And it collides with a 1,500 kilogram car, which is traveling south at 30 meters per second. Okay. And then they stick together and move as one. So before the collision, we have the momentum of each individual car. So the 2,000 kilogram car has a momentum of its mass, the 2,000 kilograms, times its velocity. Since this is moving north, we'll give it a plus sign. And we have to add to it the momentum of the other car, which is its mass times its velocity. And its velocity is southbound, is in the south direction, so we'll give it a negative sign. This has to be equal to the momentum after the collision. Now, after the collision, the two objects move as one. So we only have one object after the collision, and it has a mass of the sum of the masses of our two objects. So one's 1,500, one's 2,000. That means that the total mass of the cars combined is 3,500 kilograms. And it's moving at some velocity v, which we don't know. So what I have to do is add these two terms together and then divide by our total mass, and we can find our velocity. So if we do that, then we get negative 1.43 meters per second. So that means our velocity of our two cars stuck together is 1.43 meters per second south. Okay. Our next question asks, in an elastic collision, what quantities are conserved? In an elastic collision, this means that momentum is conserved, because momentum is always conserved in an isolated system. But also, kinetic energy is also conserved. So this is a special case of elastic collisions. In real life, there are very few elastic collisions, but sometimes billiard balls count as elastic. They're not really, because when they collide, they make sound, so some of the energy escapes, and they also heat up the ball, so some of the energy escapes that way. The only truly elastic collisions are between air molecules or fundamental particles. But okay, that's fine. The next question says, in an inelastic collision, what is conserved? We already talked about that. Only momentum. So kinetic energy is not conserved. Some of the energy gets lost in the deformation of the collision, some into sound, heat, etc. All right, so our next question says, it's Bob's turn in billiards. The cue ball is initially stationary. So this is number 7. Our initial velocity is 0. And our mass is 0.2 kilograms. And Bob uses his stick and it connects with the cue ball for 1.5 seconds. So this is the time of connection. And afterward, the velocity, the final velocity, is 2.5 meters per second. We want to know the average force with which Bob strikes the ball. Okay. Well, we know that impulse, this is a one-dimensional problem, so we'll drop the vector notation. Our impulse is equal to our change in momentum, which is equal to our mass times our change in velocity. The impulse is also equal to the integrated force over time. Now, a lot of times we don't know the actual nature of the force. We don't know the force as a function of time. So instead, we can use the average force and multiply by the time interval. Okay, so our average force times our time interval is equal to our mass times our change in velocity. But our initial velocity is 0, so this is really just our final velocity. Okay, we're looking for the average force. So we can just divide by our time interval. So our mass is 0.2 kilograms. Our final velocity was 2.5 meters per second. And we were in contact for 1.5 seconds. So that means that our average force that we applied is 0.33 newtons. This is the average force. This is the general method for finding it. We just assume instead of using the actual force as a function of time, we replace it with the average force times the interval of contact. And then we can divide our mass times our change in our velocity by the time and get the average force. All right. Our next question says, a 20 kilogram bomb initially at rest explodes and breaks into 2 pieces. The first piece is 11.2 kilograms. And it's traveling at 121 meters per second west. Right after the explosion. So we're ignoring friction. This is right after the explosion. And what is the momentum of the second piece right after the explosion again? So here, the explosion is an internal force. It's not external, which means that momentum is conserved. So the momentum before our interaction has to be equal to the sum of all of our momenta after the interaction. Okay. So before our grenade or whatever it was, our bomb was at rest, which means the initial momentum is 0. So this has to be equal to our mass times our velocity of each piece added together. This is a 1D problem. Let's call west negative and east positive. So our first piece is 11.2 kilograms. And it was traveling at 121 meters per second west. So since west is negative, we'll add a negative to it. And we have to add to that the momentum of our other piece. So that's what we're looking for. So we'll just call it P. So our P has to be 11.2 times 121 if we move it to the other side. So if we do that, then we get that the momentum of our second piece is 1,355.2 kilogram meters per second. Now, if we had been asked for the velocity instead of the momentum, we could find it by dividing by the mass. Now, it didn't tell us the mass of the second piece, but we knew that the bomb initially was 20 kilograms, and our one piece was 11.2 kilograms. That means the mass of the other piece has to be 20 minus 11.2. Because the mass has to go somewhere. It can't just disappear and vanish into nothingness. So that means that the mass of our second piece is 8.8 kilograms. So if we divide our momentum by our mass, then we're left with velocity. So our momentum, 1,355.2. If we divide by our 8.8 kilograms, you find that the velocity of the second piece is 154 meters per second. And it's positive, which means that it's going east. Okay. We could have also said that the momentum was east as well if you wanted to. All right. Now our next problem, which is number 9, says a rocket in deep space propels itself by ejecting fuel at 200 meters per second relative to itself. If the rocket's mass decreases by 57 kilograms in the time it takes to increase its velocity by 100 meters per second, what was the rocket's original mass? Now, the rocket equation that we know says that the change in the rocket's velocity is equal to the velocity at which it releases fuel relative to itself times the natural log of the ratio of the original mass to the new mass. Okay, and so we were told that it increased its velocity by 100 meters per second. We were also told that it ejects fuel at 200 meters per second relative to itself. Now, we don't know what its initial mass was, but we do know that its mass now is 57 kilograms less. It says the rocket's mass decreases by 57 kilograms, which means its mass at this time, once it's increased by 100 meters per second, is whatever its initial mass was minus 57 kilograms. So if we put this together, 100 meters per second equals 200 meters per second times the natural log of our initial mass divided by our initial mass minus 57 kilograms. Okay, well, we can get this by itself. If we divide 100 by 200, we get 0.5. So 0.5 is equal to the natural log of this thing. All right, so we can get rid of our natural log by raising both sides, e to that. So e to the 0.5 is equal to e to this natural log, but e to the log of x is just x. So this is just our m0, or m0 minus 57 kilograms. So if I multiply both sides by the denominator, I have e to the 0.5 times m0 minus 57. I'll drop the units to make it easier. Has to be equal to m0. So I want to isolate m0 so I can solve for it. So I can put the 57 times e to the 0.5 on the other side and subtract by this. So I'm left with e to the 0.5 minus 1 is equal to e to the 0.5 times 57. Sorry, this is times m0. So if I divide, then our initial mass of our rocket is e to the 0.5 times 57 divided by e to the 0.5 minus 1. So if we plug this into our calculator, and we find that our initial mass is 144.9 kilograms. Okay, so we burned off 57 kilograms of it to move 100 meters per second faster. Okay, now our long answer questions, we're up to those. So the first one says, Bob is playing pool again. He hits the cue ball, which is 0.2 kilograms, and gives it an initial velocity of 3 meters per second. And he hits a pair of balls both of which have a mass of 0.175 kilograms. The cue ball stops and one of the balls moves at 30 degrees above the direction the cue ball was initially traveling, and the second ball moves off at 25 degrees below the cue ball's initial velocity. Okay, so this is a conservation of momentum problem. So the only thing that this is an inelastic collision. It's not completely inelastic because the objects don't move together as one, but it is an inelastic collision. So what does that mean? Let's draw exactly what's happening here. We have our cue ball that's moving along. It hits a pair of balls. It doesn't tell us what direction it's moving in initially. So we can set up our coordinate system however we want to. Let's call that the X direction, whatever its initial direction was. It hits the pair of balls, it stops, and the other balls begin to move. So what direction do they move in? The first one moves at a direction of 30 degrees above. So it was initially moving in this direction. It moves off here, where this is 30 degrees. And the other ball moves off at 25 degrees below. So it moves off in this direction. Let's call this V1, and let's call this V2. Now our momentum is conserved here, which means that the sum of our initial momenta has to be equal to the sum of our final momenta. Momentum is a vector, but we can break this up into its X parts and its Y parts. So our initial X momentum has to be equal to our X momentum of ball 1 plus our X momentum of ball 2. Similarly, our initial Y momentum has to be equal to the Y momentum of ball 1 plus the Y momentum of ball 2. Okay. Now, initially, we said that our ball was only moving in the X direction, which means that our initial Y momentum is 0. And our initial X momentum is our total momentum. So in the X direction, our cue ball was 0.2 kilograms and moving at 3 meters per second. Our initial X momentum then is our 0.2 kilograms times our 3 meters per second. And that has to be equal to the mass of ball 1. They both have the same mass, so I'll just call it M, times the X part of our velocity 1. If we break our X part, or break our velocity up into an X part and a Y part, you can see that our X part is the cosine. So it's our V1 times cosine of 30 degrees, and it's going in the positive X direction. Similarly for V2, it has some mass, so we'll just call M. And the X part is also the cosine. So here's our equation for our X momentum. For Y momentum, we have 0 Y momentum initially. And this has to be equal to our mass of ball 1 times the Y part of its velocity. So this is sine. And it's going in what we call the positive Y direction, while the other ball is also sine for the Y part, but it's going in the negative. Okay, so now I have a system of equations. I have 2 equations and I have 2 unknowns. Okay, so let's put this together and rewrite our equations. I'll rewrite them without units just to make it easier. So for our X equation, we have 0.6 has to be equal to our mass. They both have the same mass, which was 0.175. And then we need the X part of the first ball's velocity plus the X part of the second ball's velocity. So this is our X equation. our y equation, it's 0 y momentum initially. Both balls have this 0.175 mass. So the y part of the first ball was v1 sine of 30, and the y part of our second ball is v2 sine of 25. So we can divide this mass away and solve for v1. So our v1 is v2 sine of 25 degrees divided by sine of 30 degrees. Now I can plug this back into our first equation here. We have that 0.6 is equal to 0.175 times v1, which is now this thing. Don't forget the cosine here. And then we have to add to it our other term. All right. Now I want to solve for v2. All right. So I can divide both sides by this 0.175. We get 3.43 is equal to v2. If I factor v2 out, we have sine of 25 over sine of 30 times cosine of 30. So that's sine of 25 over tangent of 30, since sine over cosine is tangent, plus cosine of 25, which means that the velocity of our second ball is this 3.43 divided by this thing. So the velocity of our second ball is 2.09 meters per second. If I plug this back in, the velocity of ball 1 is our 2.09 times sine of 25 over sine of 30. The velocity of our second ball then is 1.77 meters per second. Okay, so if you get a problem like this, it's essentially just a two equation, two unknown problem. And so you can just solve it. Okay, we have one last problem. It says a 1,250 kilogram car traveling north at 37 meters per second is struck by a second car traveling at 12 degrees north of west at 22 meters per second with a mass of 1,700 kilograms, and the two stick together and move as one. Right after the collision, what is the velocity of the car-car combo? So this is another inelastic collision, but this time it is a completely inelastic. And we know this because the cars stick together and move as one. Now the first car, we'll use the regular coordinate system where north is positive y, south is negative y, west is negative x, and east is positive x. It says the first car is traveling north at 37 meters per second, and it is 1,250 kilograms. And the second car is traveling 12 degrees north of west. So actually he's over here. So his velocity is like this. So it's just 12 degrees. I should have drawn him angled that way, but whatever. He's traveling at 22 meters per second. And this car is 1,700 kilograms. All right. And they stick together and move as one. So we do the same thing that we did in the last problem, only momentum is conserved. So the sum over our initial momentum have to be equal to the sum of our final momentum. It's a vector, so we need to break it down into its x and y parts. So the part of the momentum in the y direction has to be equal to, initially, you can sum, has to be equal to the final momentum in the y direction. And the same thing is true for x. Okay, so let's do the x part first. Now our first car is traveling north. That's the positive y direction. So it has no momentum in the x direction. Our second car is traveling at 22 meters per second at 12 degrees north of west. So it does have an x part of the velocity. It's this part. So it's the cosine. So our initial x momentum is the mass of our car times its velocity times cosine of 12 degrees. And this has to be equal to the x part of the momentum of the cars which have stuck together. So since they stuck together, they have a combined mass of 2950. That's just our 1700 plus our 1250. And then times some velocity in the x direction. So if I divide by 2950, I can find that the x part of our car combo's velocity is 12.4 meters per second. Okay, now we can do the same thing with y. But now both cars have a y velocity. So the y part of the momentum of our first car is its entire momentum since it's going in the positive y direction. Oh, okay, my bad. This is actually going in the negative direction, which means that our x velocity is negative since it was going west. Okay, now for the y part, our 37 meters per second is north, so it's positive. So it has a momentum of its mass times its velocity. Our second car has some y part of its velocity. It's this part, so that's sine. And it's also going north, so the positive y direction. So I have to add to it its mass times its velocity, but only the y part of it. And this has to equal the momentum after the collision in the y direction. So we use our combined mass again, times its velocity in the y direction. If I divide by this, I can find the y part of our velocity. And we can find that it's 18.3 meters per second. So our velocity then is the x part of our velocity along the x direction plus the y part of our velocity along the y direction. Okay, we could also convert this to polar if we wanted to. So I guess let's do that. So let's go to the next page. So our velocity was minus 12.4 meters per second in the x direction and 18.3 meters per second in the y direction. So if we draw this vector in its own coordinate system, it's in the negative x and positive y, which means it's in the second quadrant, and it's mostly along y. So it looks something like this. So we need to find the magnitude here and the angle here. So the magnitude is easy enough. You can use Pythagorean theorem. We have minus 12.4 meters per second squared plus 18.3 meters per second squared, the square root of that. And so we get the magnitude of our velocity is 22.1 meters per second. We can find our angle here by taking arctan. It's the arctan of the opposite side, which is our x part. Our x part is 12.4 meters per second. Remember, we never include the negative in arctan, divided by the adjacent part, which is the y part. So that's our 18.3 meters per second. So this is an angle of 34.1 degrees. So our velocity then is 22.1 meters per second at 34.1 degrees, and it's west of north. Okay. But you only have to do this if the problem specifically asks for it. If it just asks for the velocity, this format is fine. Okay, so I'll see you guys in the next video. We'll look at the next chapter.